Hi there, my name's Eric Miller, and I want to welcome you to our virtual presentation today on efficient, material selection and management and additive manufacturing. So today, what we're going to do is talk about how to get basically what we've learned at PADT and with our customers on how to pick the right materials and how to keep track of the right materials. We'll start with some introductions about who I am, who PADT is, then really kind of outline the problem, what we're trying to solve here, and then two solutions. One is kind of an effective way to select and optimize the right material. The second is to then go and track which materials you've been using. Then we'll take a little bit of time to talk about what's next in this area because as everything with additive manufacturing, it's changing rapidly. And then I've got a little resources slide at the end, and there'll also, of course, be time for questions and answers live. So, a little bit about myself. My name is Eric Miller. I'm a co founder of PADT. I got my bachelor's degree way back in 1986 from UC Berkeley, and my responsibilities at PADT are heading up basically the consulting team there, as well as marketing, which is why I'm here today, IT, HR, administration, and facilities. Besides being an owner at PADT, I do a lot of speaking and writing. I'm proud to say I've got over 200 articles in the Phoenix Business Journal, and I always welcome folks to read those. They're about all sorts of different things, including additive and running a business and all sorts of things like that. I'm very involved in the local startup community here in Arizona, working with the Arizona Commerce Authority as an entrepreneur in residence, and I belong to a angel group called ATI, where I'm a screener. And I'm also very proud to be the current chairman of the board of the Arizona Technology Council. So lots of stuff going on, very involved, as you can see, in all sorts of technology things and things in the state of Arizona business wise. About our company. So we were founded back in 1994 by four engineers who were doing turbo machinery. And at the time, um, we were using these new technologies, what we called analysis, what we kind of call numerical simulation. We were doing kind of advanced design. And then we were doing this new thing called rapid prototyping, which we now call additive manufacturing or 3D printing. So those three technologies are very new, pretty much only used in aerospace. And we thought, hey, it's the middle of a recession. Let's start a company based on those three technologies. And over the years, we've grown the company to around 90-ish employees, and we have offices across the country, mostly in the Southwest. And we not only do these things as a consulting service, but we also sell the products that we use and we provide support for those products. If you're familiar with the leaders in the industry in simulation, ANSYS and Flonex are two products we represent. And then on the additive manufacturing side, we've been a longtime partner with Stratasys. And just this year, we signed up with EOS to sell their metal additive manufacturing machines. And our latest addition to our family, it's kind of an addition, a transition. Zeiss and GOM merged, and we're now a reseller for hands-on metrology. So as you can see, kind of a broad range of products and services that really help people get their products out there. In fact, our slogan is "We make innovation work." So that's a little bit of an introduction about who we are and who I am. So what's the problem? Actually, it's multiple problems. Additive manufacturing is no longer rapid prototyping. We developed this whole world of 3D printing as a service or internally within a company really as a way to do prototyping, right? That's where it was used primarily, maybe a little bit of tooling here and there, but you really weren't making parts that were going out in the world, and you had to worry about so much about how the material behaved over the long run. And oftentimes you were more as a prototype, we were more interested in what it looked like rather than what its mechanical properties were, right? In the early days, we've been doing this for 27 years now. Every time we handed somebody a new part, they would go, "Oh, this is cool. How strong is it?" and break it, right? Because we just made out a very brittle photopolymer. Well, that's definitely changed. We have a huge selection of materials available, and we've got a lot of different technologies that we can apply to make our parts. So let's get into a little bit of detail about the problem. Um, One, especially in metal. So I'm going to be talking about both metal and plastic here and going back and forth. But in metal, we have a real problem with process failure driven by the material properties, mostly the thermal mechanical material properties, right? So we get residual stresses in our build based upon heat differences, and that can cause these kind of cracking you can see in the picture over there. So that's one problem that we have to be very aware of when we pick our materials. The next is, we have these new processes that allow us to make things that we haven't been able to make before, and also the end properties. We've got new materials, and still, in many cases, in additive manufacturing, because most additive manufacturing processes are layer driven, right? We're creating material one layer at a time. We end up with properties that aren't uniform in every direction, right? They change based upon whether you're in the plane of the build layer or not. We have issues with delamination. We have issues with being stiffer in one direction than the other. And probably the biggest problem is, over time, we've kind of developed this, I don't know, industry knowledge of which materials to use for which things, right? And that's gone now. Those material assumptions that we make when we're doing injection molding or machining or metal forming, those are no longer valid. We have to take a look at new ways of doing things. So that's part of the problem as well. And then we run, that's great if we can pretty much find an analog for a given machine for the material we would use for traditional manufacturing. But the reality is that each machine has a limited number of materials that are available for it. It's driven by the process, right? So if you're talking about, say, stereolithography, you have to have something that's a photocurable polymer, right? It's something that when you hit it with ultraviolet light, it turns from a liquid to a solid. If you're doing fused deposition modeling, it needs to be something that is a thermoplastic that you can melt that will solidify when it cools off in a strong way. Same thing for some of the new jetting technologies, right? It has to be a powder, has to be maybe uniform or non-uniform, depends on the process. And I've got to find some way to bind it together so I can make my part. Sintering's the same thing, laser powder bed's the same thing. All of these technologies drive the material options that are available because they have to work with the technology, and that's kind of the factor that makes it difficult. And I mean, another thing that's reality is, why are there limited materials? There may be a possibility for more materials, and every once in a while we'll run into a customer. It's like, hey, it would be great if we had access to this material. And we go to the people that make the material and they go, well, that's great. When you find more than one person that wants it, we'll go ahead and add it. So there has to be a demand as well. So a little bit of a chicken or the egg before they add any material. There has to be a big enough demand. And problem number four, which we'll talk about at the end of this presentation, is that um, we have to track the source, the storage, the process, and the post processes of the material, because all of those things drive the end properties, right? So when we were making a part as a fit, form, and maybe even function prototype, we didn't really care, right? We just wanted it to work. Now we have to really worry about, it's going to be out there. Now, in an airplane, that's the one extreme, and I picked that for a reason, because a lot of people are looking at replacing structural parts with 3D printed parts in an aircraft. Well, now you really have to track. You had to track anyway, but now you really have to know the whole lineage of the part. But even say you're 3D printing for a medical or for a consumer product, say a sporting goods product that's 3D printed, you still need to know, because we don't know how these are going to behave in the long run. We don't know what problems we're going to have. We don't. We're doing sporting goods. Say we're making bicycles and we're 3D printing parts in the bicycle. We won't know for a couple of years. This is all new. Whether that carbon filled polymer is going to last 30 years, or 20 years or 10 years, or is it going to crack? And so if it does, we need to know what's out there, what's there. So we just need to know. That's been a big change. And even tooling, it's true. In the past, it was so easy to make a new tool; it would just break and we'd make another one, right? But now we need to kind of know what's going on. So, what's the solution? What do we recommend to our customers? And it's to iterate on the material selection, and then kind of obvious, track things, and some suggestions will come on how to do that. So this is kind of my cartoon of what the process is to 3D print a production or maybe even a tooling part, right? So you start over here on the left with your technology. You pick your technology. I'm going to make this on this type of machine. Okay, well, of those machines, I have access to these systems within that family. Say I'm going to do metal. We have EOS. I've got an EOS, particular EOS machine. Okay, well, what materials can I run in that particular machine? Okay, so within that selection of materials, I can now make my decision. I've also got geometry, which drives the final behavior, the environment that it's going to be working in. As with any manufacturing process, but especially additive, I care about my process parameters, right? What's my build orientation? What's my layer thickness? What's my beam speed? What's my beam diameter? What's my temperature? What are the things that drive my build? Those also affect final material properties. So that goes in there as well. I do my build, then I'm going to post process it. Whether it's metal or plastic, I still got to post process it. Say it's sterile lithography, I got to put it in a curing oven, right, to get a full cure on it. How much I cure, how long I cure can actually affect the final material properties. That gives me my performance, which is what I care about. And now I got to decide, well, is that, after all those decisions and the build is done, does the material performance meet my requirements? If it is, yay, I can go. If not, it's a problem. I got to go back and build it again. And this has been kind of the traditional process in choosing materials is we just kind of try it until it works. Which is okay if you have time, or maybe your cost plus. But if you've got a budget and a schedule, it's not such a good solution. So iterating is something you have to do to get acceptable performance. Trial and error, build and bust, and time and money cost money. So what we want to do is make it as much of an informed choice up front when we pick the materials. So we want to be a little bit better instead of just saying, well, that looks okay. We want to pick the right material. And then we want to use virtual testing. I'm going to talk a little bit about both of those. So making that informed choice, remember you've got a subset of materials you can use, right? So you pick your process, you pick your machine, and then the materials that are available on that particular machine. Um, and what happens often is within that limited, so you've got those things, and then you've got responses that conflict, and you get some of these really kind of crazy Venn diagrams where, well, this one meets my requirements for, say, creep, but it does not meet my temperature requirements. So you can really end up chasing your own tail trying to do that. So we recommend a process of documenting, refining, collecting, and choosing, or if you've got a tool, refine and choose, and then use simulation and then iterate. So we'll dig a little bit deeper into those steps. So the first step is documenting, right? And this is kind of engineering 101, but sometimes because we're using traditional manufacturing, we don't have to do these things. We've kind of lost our mojo around this sort of thing. So we got to go back to principles and start by capturing the material response requirements. What Write it down. What's the stiffness, the yield, the hardness, the creep, the fatigue? And we recommend doing it in a uniform way. So every time you work on a new part, you've kind of got a matrix that you fill out so it's consistent from part to part. Then you also have to capture the environments, right? Some examples are ultraviolet radiation. Is it going to be in the sun? What's the chemical? What's the moisture? I left out temperature is a huge one as well, right? We sometimes get requirements for parts that need to work in Alaska and Baghdad, right? And two extremes in military applications. So knowing those things is really, really important. What are the other requirements? What are your cost restrictions? What's your lead time, right? You may not be able to get the material you want, or there may be some other things. If you use this material, you got to do some other things that slow it down. Geometry is also really important. You've got your initial geometry, right? What the design people came up with. This is the part I want. And you should document what you can change because you might not be able to get where you want to go with the materials you have available, but if you change the design slightly, then you can get there. It's if you're really being sophisticated, you can assign weighted importance to certain things, right? So what is the most important thing? Is it fatigue life? Is it hardness? Is it how well it resists certain environments? And also trying to find the values as min and maxes, not just, here's the yield I need. Give it a range, right? So that gives you more flexibility to find a material that hits the sweet spot. So keeping this, kind of documenting this and writing it down in a consistent way is very important. And let's assume you don't have a tool, which I'm going to talk about next, to help you make that decision. So you're going to manually pick your materials, which is fine. If you don't do it very often, it's fine. So, what you're basically going to do is refine the process, the system of materials, collect all these available materials you have available. So, go to the vendor site, find the materials they have, get the material properties. So one thing I often see is they'll use, say, the material sheet as shown in this picture, but every vendor is a little bit different. And sometimes even within a vendor, the material properties are shown in a different way, right? So what I recommend you do is you make your own little spreadsheet or document that has material properties in a consistent way. Also for that material, document what's the response to environment, how susceptible is it to temperature, what's its temperature range, what's its creep response, these sort of things, as well as kind of a ballpark look at cost and availability, right? So, well, cost doesn't have to be ballpark. You can figure out what the cost is per pound, right? So do all that. And then basically you got to sit down and close your door, put on your headphones, and walk through the choices. And you can use your own methodology of scoring it. I've seen some very sophisticated spreadsheets, or you can just kind of pick one and see if it fits. And if it doesn't, move on to the next one and see if it fits. And kind of pick the ones that work for you, and give those a try. So start with the one that looks the best. Now, if you have invested in a tool or you have access to tools, you do the same thing, right? You find the process, you find the system and the materials available, and then you put them into your tool and you put all these requirements into fields, and it will do kind of these diagrams over here on more sophisticated ones. And I'll talk about the one that we use, Granta, but you can make your own as well, whether it fits into those areas. And then there's other options out there, but the idea is to kind of create a matrix of what works and let the tool do that work for you, or at least list the options. So the two most common ones out there are the material searching tool on Serval, right? And I've got the links at the end for that. And it basically allows you to fill out a form. These are my ranges. This is what I care about. And it'll tell you what materials are a good choice, right? It's not going to tell you what's the best, but it can tell you what's a good choice. We use ANSYS Granta, and full disclosure, we also sell it, but we do like it a lot for ourselves, and we use it not just for 3D printing. We use it for a lot of different things, but it's great for 3D printing because it's often a tough choice because of the limited number of materials we have available. And you put in all these requirements, and you create these graphs where you can really find what's the right family, and then what is the right material for what you need. And Granta does have the materials that are available in the Serval database, so that's kind of a nice option for you. I keep calling it Serval, which is a cat. Senval. Sorry about that. And now here's something that, again, as I mentioned when I talked about our company, our background is really combining simulation, 3D printing, and advanced design. So needless to say, when we're trying to do advanced design with 3D printing, we're going to put simulation into that loop. And I think it's a missed step. And a lot of people maybe don't use simulation heavily in their industry or their product line, so they're not used to putting it into the loop. But oh my gosh, this can save you so much time in finding the right material. So what we like to do is basically try each material in simulation, and then so we've gone through those previous steps, 2A or 2B. We've got our list of materials. Instead of building and testing, we're going to go ahead and just run it through simulation. And we can do things like creep, we can do things like fatigue, we can do vibration, we can do all the different things that you need to do in a very inexpensive and quick way, and do a go no go on the materials from a virtual testing environment. The other thing that we can do is say, okay, well, I'm going to use this material, but it's additive manufacturing. The material properties are kind of a range. They're not a specific number, especially when you get into the directional dependency of some properties. So what we should probably do is explore the sensitivity as well. So yeah, my Young's modulus varies quite a bit based upon my orientation in the machine. So how sensitive is my part to that? Let me run it with a couple different orientations where Young's modulus is different in the different planes, right? And then I can see, well, is it a big deal or is it not a big deal? Instead of guessing or hoping, we can use simulation to answer that question early in the design process, even before we start thinking about manufacturing, when we're picking our materials. So this has been a huge differentiator for us and something I highly, highly recommend. And then last but not least is to kind of iterate. Keep trying it over and over again if you have to, if you can't get where you want to go. And part of that is changing the geometry. Now, I'm showing kind of an extreme here, an example we did for a customer of topological optimization, where we not only got it to work with the material that was available, right? So we said, these are the material we want to work. Let me back up a little bit on this, because it's kind of a different approach. Instead of saying, here's the geometry I want, which material is going to work, we said, this is the material I have to use. Here's my loads. Here's how it's attached. Now change the geometry in order to give me a shape that meets my performance requirements with the material that I have to use, right? So if I can't change the material, I can change the geometry or some combination of those. And sometimes some small changes to, just like, maybe your material just isn't getting the fatigue life you want. Change some fillets, change some holes, maybe change the load path a little bit, stiffen something up a little bit, and you can get where you need to go with the material limitations that you have with what's available in the machine you have. So I highly recommend thinking about it that way, right? If you have to fix the material, change something else in the design, maybe the geometry, maybe the loads. So that's kind of an overview of how we recommend, when you're having a tough time, you go through and pick your materials. So let's say you found the right material that works for you've used simulation to verify it. It meets your cost goals. It's available. It runs well on your machine. You figured out your post-processing steps. So you're good to go. Now, how are you going to track it? So if you're in medical aerospace, you're running under some sort of ISO requirement. You've probably already kind of figured this out, right? You've got, this is old hat. You've got a set process for traditional manufacturing. Just adopt it to your additive manufacturing process. And really the key there is to make sure your quality people understand all the steps involved, right? So, this is basic again, right? You capture where the material is coming from. You document the process the material sees when it goes from raw material to end part, right? You mark your parts in a way that you can trace it back to the material, whether that's lot or individual serial numbers. And then you use some sort of documentation, whether it's a database or paper, to go ahead and tie all this information together. So a given part, you kind of know where the material came from and what happened to it through its lifetime. And you may even want to tie in life cycle management, look at distribution and support out there. So if you've got an ERP and lifecycle tracking tool, this is all done. You just need to figure out how to get your additive manufacturing process in there. You map out your process, you sit down with your quality people, you get it in there. If you don't have a tool already, let's say you're traditionally not one of these industries that has to worry about this. You basically just buy bulk plastic and injection mold. You've got two options, right? You can get a tool and a process, or you can do manual tracking. So if you get a tool, the tool is going to drive what's going to happen. So I'm not going to really talk about that. But don't, if you don't need to do this a lot, manual tracking is a way to go. And I think nowadays we want to make everything electrical and electronic and digital. If you're not doing a lot of stuff, a paper router may be the answer. Um, what I've seen work the best is you find a quality consultant out there that's already got kind of a shrink wrap process that they've used at other companies, and they just kind of tweak it for your situation, right? If that isn't a good idea, what we recommend is kind of a basic approach, right? So first thing you need to do is make sure everything's labeled, right? It's either in a bag or a bin or a tray, or the part itself. And I give an example here of a part I'm working on that we just put the serial number into the part, right? And so we've got a little script in our CAD package that can change that number very easily, right? And you want to also know your process and capture each step. Decide if you're going to serialize or do it by lot. Lot's fine. You don't have to make everything individual, but if you want to, you can serialize as well. Make sure the end part is somehow identified as lot or serial number. If however you track parts through your additive manufacturing process, you want to go ahead and log the material information. That's kind of the key, really. What's unique about this is you're hopefully have a process logging system in place already. I made this part for this customer or for an internal customer, and here's what I did. What we're doing is adding not just the material, the raw material that went into it, but the things we did to the material along the way, what kind of pre and post processing we did. Um, the number one thing we found, and this is true whether it's additive or not, is any kind of a tracking system like this, you've got to have an enforcer, because you put it out there and it looks great, but when schedules get tough and machines acting up, you need an enforcer. You need somebody with a big stick, virtual stick, that can make sure that you're still following this process 2 years from now. Because what tends to happen is there's not a problem, the process drifts. We were in a hurry, so we skipped that. Nobody ever looked at it, and then you get a failure in the field, and you're like, okay, well, what material did we use? What else is out there that used that batch of material? And you don't have that information. So key to it is having somebody that's responsible for making sure people are doing this properly. So that's kind of our suggestions on how to solve the problem. How to pick the right material, and then how to keep track of it. Again, some basic stuff, but you got to sit down and think about it and map it out and make sure it's done. So let's talk about the future. Let's talk about what's next. So, I love buzzwords. That's sarcasm if you can't tell. But a big one right now is Industry 4.0 or Manufacturing 4.0, right? So what is it? Well, it's really putting sensors in your manufacturing systems and then connecting them so they can talk to each other and you can collect data as you go, right? So it's more automation, it's more robotics, it's more steps being done by machine rather than people, and then it's digitally controlling and monitoring and tracking that process. So AM systems are smart and integrated. They're smart already, right? They're computer driven systems. They're not necessarily integrated at this point into customer systems. There's some really good software out there that allows you to do that. Some of our larger aerospace customers have been pretty successful in creating a network of their whole process and having all the data in one central location. And the key was that it does everything automatically, right? You just run your jobs and it keeps track of stuff as it moves through the system. It's very important that the upstream be captured as well as the post processing and process monitoring while you're building, right? So one of the big benefits of this from a material standpoint is there may be some unexpected behavior during the build. Let's call it that. And if you can capture that, and then down the road, you're seeing some problems in your parts. It's like, oh, these guys aren't having the fatigue life we want. Well, it turns out there's voids. Say it's metal, right? And there's voids, and voids can happen because of the path you choose and the layer thicknesses and a bunch of other parameters in a metal build with a laser. And so capturing that in an automated system like this, when the problem comes up, you can go look it up and see, well, look at this. The laser power was varying by 10% in these builds, and all those builds are showing failures. Let me find other builds that haven't been out in the field as long, right? So these are the kind of benefits of it. It's available now, especially for larger enterprises. Um, and it's sort of fully integrated at this point. Every vendor's kind of got their own way, and they're doing better about communicating with each other. So, if you're doing a lot of additive manufacturing parts and you're already looking at doing capture and control and data tracking of your other manufacturing processes, definitely include your additive into that. I think this is going to be really important, even for the topic of today for material tracking. So, all of when I take a vat or a drum of powder, right? I'm going to scan it and put it in the system, and it's going to know that that goes into this machine. So that's all taken care of for you. So the next one is we'll actually prove this out. A lot of what we have to do now from material selection and tracking is because we don't really know what's going to happen because it's new, right? So it'll become low risk over time. And we won't have to track to the level that we track now, right? We may have to only capture anomalies and not have to worry about tracking everything. Um, and the key to getting there is tracking well now, right? So if we have the data and we're seeing good behavior out there in the real world, we can say, okay, well, we've proven this process out. We've proven this methodology out, this inspection, whatever it is, this material source. and inspection. Now we can go ahead and just assume it's going to work as long as we follow that procedure. We don't have to track it. And of course, when we get to larger production volumes, which we're starting to see, that's going to make this happen, right? So there'll be a lot of things out there, and we'll know. And we're already starting to see it in some areas. Of course, the other thing that's going to happen in the future is we're going to get more machines, different kinds of machines, totally new methods to create parts, right? Maybe they'll be less layer oriented. Maybe there'll be more uniform material properties. And all of the vendors that have existing systems are refining those. I mean, every new machine that comes out, it's a new capability, a new refinement, more accurate, whatever it is. The other thing that there's a lot of work in is post processing, and this affects material behavior, right? So we're learning, especially on the metal side, on how to post-process these parts so we can get better material properties when they come out of the machine. We're also learning on the plastic side, right? Support removal. What's the best way to do that in a way that keeps the material properties going, or doesn't break the part, right? What's the best way to maybe seal a part, right? So maybe part of the post-processing on a layered process that isn't 100% waterproof is to do some sort of a surface treatment that seals the part. Well, these are all things that people are working on. Another area to be aware of is some of these new technologies. Let's be frank, they make these ugly gray parts, right? That's the material that they're using. But what if you want green or blue or red? Well, there's new processes that allow you to dye that. So one of the inputs could have been in your material selection, this is the color I want to use. Now it's not part of a material selection, it's part of a post-processing selection. How am I going to dye that material, and what does that dye do to the process? So look for that sort of thing coming out, painting, coating, those sort of things. And simulation will also get better. We'll be able to simulate the additive manufacturing process better, as well as end part behavior better. So things that I like to recommend people pay attention to, and these could change tomorrow with some new technology. Um, a big push in the industry is this powder bed fusion or bonding, right? So I take a powder, whether it's plastic or metal, and I somehow get it to stick together to make a green part, and then I put it into a sintering oven and I sinter the part. Well, from a material standpoint, there's a big journey from those raw materials to that final sintered part. And what are the final properties? Sintering is a high shrinkage process, and controlling that and dealing with the stresses in that is really hard. We're just getting our hands around simulation for that. But when that's cracked, when we're able to make accurate parts using sintering and strong parts using sintering, that's gonna take over a lot of processes. Also, I have mentioned this a couple times, technologies that don't have to build one plane at a time. I talked about, kind of making a powder part and sintering, but there's going to be more green part processes. Maybe it's a plastic photopolymer that makes a green part, a part that's not 100% done, and then you have another step that cures it. So multi-step processes are going to become more popular. And also, there's a lot of people trying to find ways to use traditional manufacturing materials in additive manufacturing. And a great example of that is the very large fuse deposition modelers, right? So these are big machines where you take off-the-shelf plastic pellets and you pour them into a giant hopper and you melt them and you extrude them out of a big nozzle, right? And you make tooling, say, for layup of composites. It's great because they're using traditional materials. It's not a special build of material. It's just off the shelf material. And we hope to see more of that with powder metals and other processes to where we're not using special materials anymore. And that gives us a wider range of selections. Which brings us to more materials, right? This is where the biggest change has happened, and this is where the biggest change will happen in the future. Existing AM processes are going to, the market's going to demand more materials, right? A big thing a couple years ago was somebody came out with a continuous fiber carbon, right, in the middle of these plastic polymers that are extruded. Well, everybody said that's great, but what I really want is chop fiber. So there's been the huge explosion of chopping things up and putting them into the polymer and then extruding it. And we personally we do nylon filled with carbon. We've got ABS filled with carbon. We've seen some other fillers as well that we've played with. There's a lot of options out there, and it can really get you closer to the material properties you want using additive manufacturing. And as we get wider adoption, the cost is going to come down and we'll get greater variety as well. There's also going to be some new processes that open up new materials. Um, there's I need to follow up on this, but a couple of years ago, I talked to a gentleman that was working, I think it was at 3M, on a Teflon based, PTFD based process. So wouldn't it be great to 3D print Teflon parts? Well, they've got a machine that does it. I don't know that it's commercially available. I think they do it as a service. The last time I talked to them, but these things are becoming available, and there'll be other people, maybe on the material side, maybe on the machine side, but coming up with new materials that will allow us to have greater flexibility as time goes by. And one thing that I always recommend is to also look at digital materials. So if you're familiar with the PolyJet technology from Stratasys, we've got multiple print heads, right? We're inkjet printing a photopolymer and then curing it with light. Well, we can mix those to get different colors, but we can also mix them to get the exact material properties we want. So back to that whole process before of picking the material, once I've said I'm going to use a digital material and I know that the range of those materials are going to work, I can really dial in the stiffness, the color, the transparency, other additives that I can put into the process. And I expect to see more of that. I expect to see metals being mixed or additives into the building process that change the behavior of the material. So there's a lot coming along the lines of while you're building the part, you're changing the material properties, and not just for an entire build, but within the geometry of a build. So pay attention to that. And then when you are picking your additive manufacturing technologies, it's probably better to invest in machines that allow you to add new materials. You might want to save a bit of money and go, well, this machine allows me to add more materials in the future, but this one just runs ABS, and all I really need is ABS. And guess what? You probably need other materials as time goes by. So do think about that long-term flexibility when you pick your machines, so you can run different materials. So it wouldn't be a presentation in 2021 without talking about artificial intelligence, right? So where does it fit into this? Well, the process that we talked about, where you use a tool to create that Venn diagram, or maybe you just put in a form and it lists these are the materials that fit that form. That can all be changed into rules-based selection. So not necessarily machine learning, but asking you, what are your rules? What do you care about? And creating algorithms that use that to make a more intelligent decision. So look for that to come out with the tools that we already have. I expect that to be added to those tools to make them smarter. And then over time, we should be able to do machine learning. As we've got more data out there in the field of parts being made, we should be able to take that back and look at how it behaves and make better decisions using machine learning algorithms. The key to all of this is good inputs. So that doesn't change. And hopefully we'll see this come on the market very soon. There may even be some people out there offering this up right now that I'm not aware of. So that's what I have to talk about the future. Resource wise, here's some information about PADT. Please check out our blog. We also have a site that we put out there for the community called 3dprintingglossary.com. And we highly recommend you use that if you want to know the actual definition of different things in the world of additive manufacturing. All of the additive manufacturing vendors have some good sites, the industrial ones. Of course, we use Stratasys and EOS, so I recommend you check out their material information. 3D Systems also has some good information. We do run 3D Systems machines at PADT, so we use their material finder as well. Anybody that's got an industrial system out there is going to have a materials resource. Also, what's on their website is kind of what marketing lets them put out. If you're really struggling with materials, reach out to the company and get in touch with their technical experts on material selection. Not only can they help you answer these questions, but often they have materials that aren't necessarily commercially available, but they'll do under a beta program or something like that, that might get you what you want, or they may have recommendations you're not aware of, maybe post-processing, other things you can do to get the properties you want. So, if you're struggling with materials, go to whoever you bought your machine from. If it's PADT, give us a call. We'll connect you with the experts on the materials. Also, check out the ANSYS products materials page on the Granta product. Highly recommend it if you're dealing with a lot of materials. It's a great tool. The Senval, not Serval, but Senval database is available on the web as well. Fantastic. NIST has got a fairly robust, it's not as complete maybe as the other one, of material properties for additive manufacturing. And the UL is getting into this area. And they've got a thing called IDES that they put together that's a product browser that lets you pick materials for additive manufacturing. Please do feel free to reach out to me at eric.miller@padtinc.com or visit our website at padtinc.com. I want to thank you for spending a couple minutes with me in this virtual environment, and I wish you luck in finding the right material for your next additive manufacturing project.